differently and so forth. And we have one more chapter to do within the matrix unit. Except it's only going to take us 1 week. Just this week will be all we spend on chapter 10. It's an application of the matrix stuff that we've been doing. An application to systems of linear differential equations. Now, we have talked about systems of linear differential equations already in this course. Do you remember the technique that we applied at one point to solve systems of linear differential equations? We spent about 10 minutes on it, so admittedly it's not the thing uppermost in your mind from this class. Do you remember how we solve systems of linear differential equations? What I have in mind is the Laplace transform. We use that to solve a single differential equation, but we also talked about how applying the Laplace transform to a system of differential equations would give us a system of algebraic equations, then you solve that system, pull back, etc. So we have talked about this before very briefly, and we're going to spend another week on it. It's an important topic. A system of differential equations has to do with things that are interrelated in their rates of change. And we'll spend a little more time on that thought toward the end of the week. So, section 10.1 is called Theory of Linear Systems. So we're going to go through section 1 fairly quickly, talk about theory, can't even spell, theory, there we go. And then section 2 has to do with actually getting in there and doing the solving. So we'll spend the rest of today then and all of Thursday on section 2 on solving. But first we do need to set out some theory. So first I want to draw an analogy between what we have been doing and now what we're going to do. So our previous situation, we spent a lot of time in chapter 8 talking about a system of linear algebraic equations. And of course, we spent time working with matrix solutions. But let's talk about what the nature of such a solution is. If I solve a system of equations, algebraic equations, well, let's back up even further. What kind of a thing am I looking for if I solve a single algebraic equation? X plus 3 equals 11. What am I looking for? What kind of a thing do I get as an answer? A number. Okay? If I solve a differential equation, I'm no longer looking for a number. I'm looking for a expression. That's a little vague. The answer to an algebraic equation is a number. The answer to a differential equation is a equation, line, derivative. I'm looking for the word function. You're looking for function so that if you take this, the derivative of that function, plug it in, you get a true statement. So now we get to a system of algebraic equations. So we're back thinking about numbers instead of functions. And the solution is, well, we're usually looking to solve for x1, x2, x3, x4, and so forth. So we're after a whole vector of numbers. So your solution for a system of algebraic equations, and this is the kind of thing we've been spending a lot of time on, is a vector of numbers. And now our new situation, we are trying to solve the system of linear, and we're going to be somewhat restricted or timid in our quest. We're not going to satisfy or try to solve higher order differential equations, just first order ones. So we're after solving a system of linear first order differential equations as opposed to algebraic equations. So what kind of solutions will we get? Instead of a vector of numbers, a vector of functions, because the solutions to differential equations are functions. So we are after a vector, and the notation will be x1 of t down through xn of t of functions rather than numbers. So this is a big picture kind of a thing. I don't like it if students just learn how to compute and they don't even realize what it is they're looking for. So make sure you understand what we're after. We are going to throw in one simplifying assumption. I made a big deal the first day we started talking about matrices, or rather about systems of matrix equations, that in real life you don't always get the same number of equations as you have unknowns. Well, here we're going to assume that we will. So our simplifying assumption will be the number of equations matches the number of unknown functions. And that's simply because the solution method we're going to come up with only works for square matrices, and so that's an assumption that we're going to have to put in order to solve this kind of situation. If you didn't have that, you would just have to come up with another technique, but the technique we're going to look at requires this. So let's get specific. Specifically, consider the following. Linear system of DEs. So here's what they will look like. x1 prime of t equals a11 x1 of t plus dot 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 plus a sub 1n x sub n of t plus possibly an f1 of t, etc., down through xn prime of t equals an1 x1 of t plus dot 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 plus a sub n x sub n of t plus potentially an f sub n of t. Now it's really easy to let your eyes just kind of glaze over at something like that. You copy it down and it looks totally meaningless. Don't do that. Remember what a derivative means. A derivative means a rate of change. So we're talking about how things change over time. And we're saying that x1, how it changes over time, doesn't only depend on itself, it also depends on a lot of other factors, these other x's. And again, we'll talk more about examples toward the end of the week. Each of these things, whatever they happen to be, depends not only on itself, its rate of change depends on what's going on with all the others over time. So you have a crazy, dynamical, interwoven system going on here as time passes. These f's are just some extra functions of time that don't involve any of the x's. They may or may not be there. In fact, I could mention that right now. If f1 of t through f sub n of t are all zero functions, the system is, well, what would be a nice word to attach there? Basically, when something or other is all zeros, we usually call it. They would all be zero functions, but then the whole system would be homogeneous or homogeneous, however you like to pronounce it. Homogeneous. And very often when you have a homogeneous system, it is easier to solve. Okay, so let's take this thing, and I hope it's not at all surprising to you that we're going to put it in matrix form. It seems to beg to be put into matrix form to organize all that information. And here's what the matrix form looks like. Big X prime of t equals big A times big X of t plus big F of t Now, most of these guys are going to be column matrices, the F, the X prime. A is the only one that's fat. It's a square matrix. So A is basically the matrix full of coefficients. A1, 1 out through A1, and down to AN1 over to ANN. So no surprise there, just the matrix full of coefficients. Big X of t is the thing we're after. It's a vector of functions. So that is our little x1 of t down through little xn of t. That's what we're after. That's what we're solving for. A matrix, or rather a vector of functions. And big F of t is nothing more than a compilation of these little f functions, f1 of t through f sub n of t. And if you look at this matrix equation, hopefully it makes sense to you that it faithfully reflects the system up there. For example, if I multiply A by X, I'll get A11 X1, blah, 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 plus A1N through XNT, plus the F equals the derivative, and that's exactly what the original system is saying. So this is a good matrix setup because it faithfully expresses what we began with. Let's pause for a little easy example before we go on to some theory. So far, we're really just doing setup. But we'll make sure that you can handle this little task. I'm going to give you a system of differential equations, and I want you to write it in matrix form. So the first differential equation is x prime equals negative x plus 3y. The second one is y prime equals x plus e to the negative t. And all we're going to do is write the very same system in a different form. So the form is supposed to look like x prime of t. Here, x prime is just a 2 by 1 vector, x of t, y of t. That should not be x of y, but x of t, or we'll just call it prime. X prime of t, y prime of t equals, and then just go ahead and fill in the rest of it. Make sure you see how it all fits together. And of course, this guy here is simply your unknown function, so that again is the x of t, y of t. What goes in here? Tell me what four numbers. Negative 3, 1, 0. There you go. You did pick up on the fact that there was a no y term here. So negative 1, 0. And then over here is where the leftover stuff goes, the stuff that doesn't involve x or y. So that will be top component 0 and bottom component at e to the negative t. So it's simply another representation, and it gives us a way then to use all the matrix functionality that we've learned over the past several weeks. Let me show you one other way to write it. Often, instead of saying little x prime of t, little y prime of t, we'll just say big X prime equals, and then we have our A matrix the same, and then big X plus the leftover stuff. But when the form is given to you like this, I want you to remember that those x's are not just functions themselves, but they're vectors of functions. So keep in mind that that always means a number of components in your solution. Questions so far? It's not terribly deep, just stuff we have to establish before we really get started. Okay, next idea, now we get into the theory. Principle of superposition. This thing just pops in so many contexts. We just did it in EnMath B yesterday when we were talking about solving partial differential equations, which is more complicated than solving a system of ODEs. But the basic idea of it remains the same. We're regardless of the context. Suppose x1 of t and x2 of t. So again, read those as column vectors. Don't just look at it as one thing. Suppose they are solution vectors for the homogeneous linear system. Now, all along I've been using the word linear. Linear just means that everything in sight is to the first power. We don't have any squares, we don't have any crazy exponentials or trig going on. It's all just every variable to the first power. So that's what makes it linear. Homogeneous, of course, means that all the f stuff over on the back end is 0. We don't have any interesting leftovers. So suppose these are solution vectors for the homogeneous linear system. X prime of t equals a times x of t. And you'll notice I didn't put a plus f of t on the back end simply because I'm going with a homogeneous system at the moment. Then, now whether or not you've seen the principle of superposition in this context, I hope that you have seen it in other contexts. So tell me what the conclusion is. And I could really pick on anybody I had in EnMath B last semester because we certainly talked about it there. But I don't want to pick on anybody. Who knows? If I have some solutions to a linear, homogeneous, whatever the context, the conclusion is okay, I guess maybe we're not familiar about it or you're all just shy or all tired or something. Then, any linear combination don't mind if I raise the board here. If I'm hiding something you need, I'll get it back in a moment. Any linear combination, big X of t, which is C1 x1 of t plus C2 x2 of t, is, does that help you? Any linear combination is also a solution. There you go. It's also a solution. So basically, the principle of superposition, first of all, this business about homogeneous linear, those are essential requirements. If you take out either homogeneous or linear, it doesn't work anymore. But if you have those two things, linear combinations of solutions give you more solutions. Now, here's what the principle of superposition does not say. And it's very easy to read it into it, and it does not say it. It does not say when you do linear combinations, you get all solutions. Sometimes you do because of other situations, other theorems, but not always. And even when you do, the principle of superposition isn't saying that. Other theorems might tell you that. So it does not say you get all solutions this way. It just says you get more solutions this way. And it's still an open question whether you get all of them. So that means we're not done with our theory. Because we want to know. Not just that we have some solutions, we want to know when we have them all. We want to know when the job is done. So we need more theorems. And lucky you, I've got 2 more theorems here. Theorem 1. The set of solutions of an n by n homogeneous linear system and that's the system then that looks like big X prime of t equals a times x of t, same thing over there, still assuming homogeneous, is a vector space of dimension n. And you may think, okay, big deal, but this really tells us a lot because it basically simply says that if we can find a basis of solutions, what things, well, let's back up and remember what a basis is. What three things has to be true about a basis? What's one of them?
One of them is that it has to be a member of the set that it's the basis of.
Okay, so everything in your basis better come from the set that you started with, so that in idea. What else? What else has to be true of a basis?
It spans.
It spans and, Rachel?
Linearly independent.
Linearly independent. So there are the three things. So what this is saying is if we can find a basis, then we will, and the key thing really is spanning. Spanning means you get everything you want. That's the same kind of thing as saying general solution. If we can find a basis, then we know that we get everything, and we are done with the job and we can move on. So this is a nice theorem because it says if you've got an n by n, in other words, n equations, n unknown functions, if it's homogeneous linear, then if we can find a basis for that, we will know we have the general solution. Theorem 2 is even nicer because it essentially says all we have to get are 2 out of 3 of those, a specific 2 out of 3. So here we go. If x1 of t, comma, x sub n of t is a set of n linearly independent solutions to the system x prime of t equals a times x of t, then, so same system, same set of homogeneous linear, blah, blah, blah. Now, which 2 of the 3 have I hypothesized here? Clearly linearly independent. What's the other one you see? It's a little more hidden. So I'm assuming that we have a linearly independent set, and every element of the set is what? It's a solution. So in other words, it's in the set we're talking about. So we have the in thing, we have the linearly independent thing. It turns out that then this thing also spans. So this is a lovely thing. Then these n functions span the vector space of solutions. So we get that one for free. So they form a what for this space? What word can I fill in there? Each thing is in the space, the set spans, it's linearly independent, therefore it is a basis. So they form a basis. So this is lovely because if we have the in and we have the independence for free, we get the spanning. And therefore we have the general solution. So thus, the general solution, by the way, what does the term general solution mean? General solution means the set of, well, you guys are giving me a lot of good true-false stuff to put on the next exam. What do these things mean? The general solution means the set of all solutions, all possible solutions. We want to know when we're done with the job. We want to know when we have everything. So thus, the general solution, which is the complete set of solutions, is this. X of t equals the set of all linear combinations of these n functions. And that then completes the theory. So try not just to write all that down, try to grab onto the impact of it. The impact of it is when we are actually trying to solve, And remember, we're trying to solve for all solutions. This is what we want, the general solution. Our task is to find n linearly independent solutions. If we can accomplish that task, then we will be done with the job, because the set of all solutions will be gotten by linear combinations of those n independent solutions. Do you have any questions? Okay, so that leaves open a huge question, and that is, how do we find those n linearly independent solutions? That gets into what we often like better, and that's just tell me how to compute, and I'll compute. But I don't just want you to compute, I want you to understand the point of it all. But let's start digging into that computation question. So the rest of today and into Thursday will be all about how do we make that work. So section 10.2 is called homogeneous linear systems. Actually, we're going to be talking about the computation the rest of today and part way into Thursday. Most of Thursday actually is going to be spent drawing pictures. So if you like drawing pictures, be sure to come. Okay, so first sentence is just saying we have the same setup as before. Consider the system of DEs x prime equals AX. So linear, homogeneous collection of differential equations. And let me mention one thing I've mentioned a number of times in the past few weeks. The entries of A are all real. The reason I have to mention that, complex numbers are going to show up again, but we're not inviting them in to begin with. We're starting always with real entries. So let's try to just figure out what might work. We're going to do a little bit of mathematical playtime here. So note that if n equals 1, boring situation, one equation, one unknown function, basically means we have one differential equation only. So then the system, quote unquote, not much of a system since it's only one thing, reduces to the single differential equation given by x prime equals some number a times x. X here is a function of t. Still think of that as x prime of t equals a number times x of t. Now the reason I'm reducing down to a single one is because you know how to solve a single differential equation. And we can then get hints from that as to what to do when we have a larger system. So, how would you go about solving that? Any big ideas? Yes,
We
Rudy.
treat x prime as dx dt.
Okay.
And put divide by x on each side and
Mhm.
multiply by dt on each side.
Okay.
And integrate.
So essentially you're thinking of the technique of separation of variables.
Yeah.
And that's an excellent one we can do. I'm going to mention EnMath B again. We're just now reviewing, or just have reviewed, 3 techniques for solving first order differential equations. One of them is separation of variables. One of them is using an integrating factor. And there's one more that's even simpler than the other 2.
Characteristic.
Characteristic equation. So I'm going to rewrite this. I'm going to go with that one because it's the quickest and easiest. So this could be rewritten x prime minus ax equals 0. And the easiest way to solve it is using the characteristic equation. Depending on what book or teacher you had for differential equations, sometimes it's called the associated polynomial. Characteristic equation is simply r minus a equals 0. You pull that out of there. It's not as interesting as the characteristic equation for a second order, but it still works. We solve for the one and only root of the characteristic equation. And hopefully you know from that how to find the general solution. And I'm going to write it as x of t equals c times what? What does that single real root tell you about the solutions of this equation? it's easier if you have more than one. Think second order. If I got distinct real roots, like 2 and a 3, that would lead to what solutions? E to the 2t, e to the 3t, and so forth. But you don't have to have anything repeated. You can just say c e to the at. The point is you get exponential kinds of solutions. Hopefully that rings a little bit of a bell. If not, characteristic equation might be something that you would want to review. So that's what happens if I have just one very simple linear differential equation with constant coefficients. But it leads us to suspect that exponential solutions might work for larger values of n. So there's the question, could exponential solutions work for n greater than 1 as well? And the answer to that is sometimes. Let's go ahead and explore it and see what it would look like if the solutions are exponential. So suppose there is a solution, and this is still mathematical playtime. Some people think of mathematics as all cut and dry, black and white. At some point, somebody had to be creative and figure this stuff out. This is the kind of way you think through stuff. Suppose there is a solution of the form. We're just hypothesizing a possible solution. X equals v e to the RT for some real number R and some non-zero constant vector v. In other words, suppose, so I'm just saying, let's imagine that there's an exponential solution. See if I can play with that and come up with any ideas about it. So in other words, I'm going to suppose that my solution, and remember again that x is a vertical thing, it's a column vector. So I'm going to imagine that it's made up of some real numbers. This is my capital V, it also is a column vector, times an exponential. So in other words, something like V1 e to the RT down through V sub n e to the RT. I'm just hypothesizing, I'm just playing. If that's really a solution, let's see what happens. So here's my system. X prime equals a times x. Let's go ahead and plug it in and see if I can come up with any ideas. So I'm going to need the derivative. If my column vector x looks like this, then what's going to be the first component of its derivative? All you do is differentiate component by component with respect to t, so I get what?
RV1.
Yeah, RV1 times e to the RT, and we continue to differentiate. The bottom one would be R v sub n e to the RT. All right, we're ready to plug and see what happens. So plug into the system, and the system is, again, what I kind of boxed off over there. The derivative equals the coefficient matrix times our vector x. So I'm going to write down the derivative vector, RV1 e to the RT down through RV sub n e to the RT. It's kind of starting to look fat, but it's really still just an n by 1. It's a skinny vector. Equals my given matrix A, that's a given matrix of just real numbers, times the column vector x, which is this one right here, V1 e to the RT, down through V sub n e to the RT. So my point so far is, if there's a solution of this form, and I plug it in, this is what it looks like. Let's try to simplify this a little bit and see if I can get anything out of it. Is there anything that I could pull out of this? A scalar kind of a thing that I could pull out of this vector. certainly. Anything else? Yeah, we can even pull out the e to the RT. That's what we would think of as a scalar function. But it's common to everything in here, so I can pull out the r. I can leave the v1 through vn, pull out the e to the RT on the back end, and that's going to equal a times, can I pull anything out of this one? Same as before, which part can I pull out? E to the RT. So I'm going to have my v1 through v sub n, e to the RT. Now, let's see what conclusions I can draw from that. First of all, what size is A? Remember, it's that fat coefficient matrix, so its size is n by n. So it's an n by n matrix. What do I get if I multiply an n by n matrix by an n by 1? I get an n by 1, so there it is. That's just a scalar. Those things are just scalar functions. So basically on both sides of this equation, I have an n by 1 matrix. Would it be legitimate to divide out the e to the RT? It's just a scalar function. And remember, the output of the exponential function is always positive. We would never run into division by 0. So it is legit to just divide that out. On the other hand, can I divide out the common vector? Certainly not. That would make no sense. Then I'd be left with a number equals a matrix. That's not making sense. So this matrix times that vector is that vector, but that doesn't mean we can divide that out. So let's divide out what we can. But be careful and not do anything silly. So I'm going to divide out that e thing, and I'm also going to write the right-hand side now on the left. What I will get then is AV equals RV. The e's are going away. We get the matrix A times the vector V equals the number R times the vector V. Have you ever seen that kind of setup before? Matrix times a vector equals a multiple of that vector. Rachel?
It's like that eigenvalue.
It's all eigen stuff. What we have discovered is that we have an eigenvalue, eigenvector relationship. Matrix A times the vector V gives us a multiple of the vector V. So we can conclude thus V is an eigenvector of A corresponding to the eigenvalue R. And all of a sudden, all this theory that we came up with over the last few weeks seems to be relevant, seems to be something that we can bring to bear on the solution of this differential equation. So, here's what we know so far. And remember, this was just playtime. This was not really proving anything. But I think we can make this observation anyway. The eigenvalues and eigenvectors of A, and remember A is just this coefficient matrix, thus seem to be related to the solutions of our equation x prime equals a times x. And so this gives us a direction to go in. It gives us an avenue for further exploration. And I'm just going to say, let's consider the cases. Now, what do I mean by cases? Well, what I mean by cases is A seems to be the focal point, this matrix of coefficients. Let's find its eigenvalues and then think about what kinds of forms those eigenvalues can take. That's what I mean by cases. So case 1 is going to be the nicest case, distinct real eigenvalues. So in other words, if we find the eigenvalues of A, they're all distinct, they're all real. The reason I say it's the nicest case is because in a way we've already solved it. That was kind of my hidden assumption up here. So let's call them lambda 1 through lambda p. Now you may wonder why I don't say lambda 1 through lambda n. Well, it could be that, suppose you have a 10 by 10 matrix, maybe 6 of them are distinct and real, and then maybe you have some repeated ones, and maybe you have some complex ones. A lot of things can happen. But for now, we're just thinking about the distinct real ones with eigenvectors, capital K1 through capital K2. So we're just going to suppose that out of our collection of eigenvalues, we have some distinct real ones. We find the eigenvectors, they turn out to be these Ks, and we're actually basically done with this case. We will come up with some linearly independent solutions simply by taking a look at this top board and working backwards. So working backwards from the eigenvalue, eigenvector idea, moving our way up the board, all of that came from this fundamental assumption that we had exponential solutions. And that assumption led to the little r being the eigenvalue and the v being the eigenvector. And so now working backwards, we can say here are our solutions of that form. Eigenvector times e to the eigenvalue times t. So with these eigenvalues and eigenvectors, it would be k1 e to the lambda 1 t, etc., dot, 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 out through k sub p, e to the lambda sub p t. And that just came from doing our mathematical playtime backwards. Any questions on that idea? Does that all hang together more or less? Okay. Let's do one example and see how it actually plays out. It's always nice to look at something specific and see how it works after we've seen all this theory. So here's an example. System of differential equations. dx dt equals 5x minus 8y. Y dt equals 3x minus 9y. So it fits the form. We have two equations, two unknowns. It's homogeneous. I don't have any extra t stuff hanging off on the back end here. Linear, constant coefficients, everything is just as we've been talking about. So, see if you can write it in matrix form. Basically always the same form, x prime equals, and then you just pop in all those coefficient numbers in there, times x. So hopefully you're just writing 5, negative 8, 3, negative 9. And if you remember that x really means the vector xy, and x prime really means the vector x prime, y prime, then sure enough we have 5x minus 8y equals x prime, 3x minus 9y equals y prime. So that is a faithful representation of this system of equations. But that means then that our coefficient matrix is 5, negative 8, 3, negative 9. And the idea is that now we find the eigenvalues and eigenvectors and see where that takes us. Being the lazy person that I am, I don't want to find the eigenvalues and eigenvectors. So I picked an example that we've already done. So this is example 1 from back in section 8A. And that means we already know the eigenvalues and eigenvectors. We have already worked them out. Possibly these will look familiar to you. Lambda 1 equals 3, going with k1 equals 4, 1. Lambda 2 is negative 7. going with K2 equals 2, 3. That's the hard part of the work. We're skipping the hard work of finding eigenvalues and eigenvectors. Once we know them, then all we do is say, well, what do you know? We've got distinct real eigenvalues, 3 and -7, so we're going to get exponential solutions. And they will look like this. Big X1, and I'm going to keep reminding you that that stands for the column vector, little x, little y, will be eigenvector times e to the eigenvalue times t. So the eigenvector for 1 times e to the 3t. We just pick on the eigenvalue, e to the 3t. And if we would multiply that scalar function in, there would be our solution. X equals 4e to the 3t, y equals e to the 3t. That's the first solution we get out of it. Second solution we get out of it is, again, bearing in mind that that's a little x, little y. Will you do it? Just follow the same pattern. Write down the eigenvector, multiply by e to the eigenvalue times t, and then put it all together. Multiply in that exponential. So from the second pair, we get the 2, 3, e to the -7t, which gives us the solution 2e to the, -7t, and 3e to the -7t. Then we apply the theory that we talked about half an hour ago. I have a 2x2 system. I now have 2 linearly independent solutions. How do I get the general solution? In other words, how do I get the set of all solutions?
Use the principle of superposition.
Okay, but it's even stronger than the principle of superposition. Remember, the principle of superposition only tells us that if I do linear combinations, I'll get more solutions. We're going to be even bolder and use theorem 2. Theorem 2 said I get the general solution that way. In other words, the set of all solutions. So my full solution will be this thing, C1 for 1 e to the 3t plus C2 2, 3 e to the -7t. Or again, you could wish in the exponentials if you prefer. So it's a very bold, strong thing to say this is the general solution, this is the sum total of solutions, there are no others. Any questions on solving that example? After all that theory, it really isn't too bad when you actually make it happen. Okay, you're all probably wanting a break. I'll give you one pretty soon. Sorry about that. If you're desperate, go. I won't watch. But I would like to do a check, because I think it's interesting to see that this really does give you something real. It does give you genuine solutions. So let's just briefly, this will only take a couple of minutes. Let's check the first one. Check the first of these 2 examples, or excuse me, the first of the 2 basic solutions. So the first one says xy equals 4e to the 3t, e to the 3t. So in other words, x is 4e to the 3t, y equals e to the 3t. And what I want to see is then, do we really satisfy that pair of differential equations up at the top? I want to see if it really does work. So looking at the first differential equation at the top, we're interested in 5x minus 8y. Well, let's see. If I do 5x minus 8y, 5x is 20 e to the 3t, minus, and then we'll have minus 8 e to the 3t. Subtract 20 minus 8, that gives me 12 e to the 3t. That's supposed to be dx dt. Is it? Here's x. Do we really get dx dt? Sure enough, it works. So this is dx dt Check. Now let's check the second equation. 3x minus 9y. You work this one out. It's not that scary. Multiply x by 3, multiply y by 9, subtract, work it out. See if you really do get what you're supposed to get. The top says dy dt equals 3x minus 9y. So hopefully you are doing, let's see, that's 12 e to the 3t minus 9 e to the 3t, which equals 3 e to the 3t. And is that really dy dt? It sure is. So the system works. We did get genuine solutions. But that just checks those individual solutions, or actually just checked x1. You would have to check x2. But it's still very significant that the theory says this doesn't just give us some solutions, it gives us everything. Any questions? Okay, take a break. And if someone can be so kind as to bring down the attendance sheet, I think there are a few people that will want to sign that. We're trying to solve these systems of differential equations. Eigenvalues and eigenvectors seem to matter. So I said let's consider the cases. Case 1 was if we get real distinct eigenvalues. What would some of the other cases be? What else could pop up when we solve for eigenvalues? Yeah, Ben. Repeated, and what's the other case? Complex. So those are the things we have to deal with. What if we get complex eigenvalues? What if we get repeated eigenvalues? So we're going to tackle the complex idea next. Now suppose that A has complex. Now I do want to remind you of one thing. If we begin with real numbers in A and we get complex eigenvalues, then how do they come at us? They're not just totally random, but they come at us in conjugate pairs. So suppose that A has complex conjugate eigenvalues, which we will call lambda 1. We'll say that's alpha plus beta I. And lambda 2 then would be what? What's the conjugate of that? Alpha minus beta I. The real part stays the same. The complex part gets a negative attached. With corresponding eigenvectors, and as you know from experience, when you solve for the eigenvectors that go with complex eigenvalues, sure enough you get complex eigenvectors. They also come in conjugate pairs. So we'll call them K1, and I'm going to write that as B1 plus B2I, and K2 then, the complex conjugate of that is B1 minus B2I. And recognize those, of course, as column vectors. The K's, the B's, those are all column vectors. Now, where do we start? Well, the most reasonable way to start is to try to do what we did over here, to try to mimic what happened for the real eigenvalues and eigenvectors. And then just see what happens. So this is, again, a little bit of mathematical playtime. If we proceed as above, we get, well, the solutions we get are going to be complex functions or complex solutions. And they would look like this. K1 e to the lambda 1t. That's at least the first one. So all I'm doing is the very naive thing of just saying, all right, let's follow the same process. Trouble is I've got complex numbers in there. So K1 e to the lambda 1t is the same as B1 plus B2I. That's how we're rewriting the K1. E to the alpha plus beta I times t. And that's the first one. The second one would be similar. K2 e to the lambda 2t would be B1 minus B2I, the complex conjugate of the first one, times e to the alpha minus beta I t. So we look at that and we say, okay, fine, we very formally did the same thing as we did before, but we don't like it. These are complex things, there are complex numbers all over the place. So now I'm just going to complain a little, but we want real solutions. If we begin with real differential equations, we certainly ought to be able to get real solutions. So, some of you have an idea of what we're going to do next. How do we take these crazy things that involve complex numbers, and the trouble is they don't only involve complex numbers on the baseline, we've even got complex numbers up in the exponent. What fabulous thing do we apply to help us with this? Do you know? What little expression, what was that? What's that? Yeah, you're going to get sines and cosines using whose formula? What formula? Logan? There you go. Euler's formula is what I'm looking for. Some of you may remember that you've done similar things like this in your differential equations class or in other classes. So Euler's formula is a formula that takes an expression e to the I theta, where you have that complex imaginary number up in the power, and rewrites it how? Do you remember? First part is,
Cosine theta.
there you go.
Plus I sine theta.
Cosine theta plus I sine theta is exactly it. Now, just as a little side note, does anybody have any idea whatsoever how you would prove that that's a valid expression? I mean, it's pretty weird looking. Any ideas? You actually prove it using power series. You look at the power series for e to the I theta, and you have all these i's and I squareds and I to the thirds and so forth, and you kind of simplify and you separate things out, and what do you know? You get the power series for cosine plus I times the power series for sine. So it's weird, but it really does have some basis in real math stuff. So let's apply it. Let's go back to our k1 e to the lambda 1 t. So far we've said that that is, here it's fleshed out a little bit over there, b1 plus b2i times, now I'm going to take that e part and split it apart, because part of the e stuff is already real, which we like, part of it is imaginary, which we don't like. So I could write that as e to the what, and split it apart how? E to the alpha t, good for you, e to the alpha t times, and that's important because even though it's a plus in the power, it becomes a times on the baseline, times e to the, and then we want the rest of it, that beta it. E to the app times e to the bit. Okay, so there is an expression for our solution. We still don't like it because it's still complex, but let's keep going. I'm going to repeat b1 plus b2i. I'm going to save the e to the alpha t and put it at the back end. Right here I'm going to work out e to the beta it by Euler's formula. So if you look at Euler's formula, the theta there corresponds to what here? The theta there is beta t, the I is just I, so it's going to be the cosine of beta t plus I times the sine of beta t. And then I don't want to forget my e to the alpha t, it needs to hang around even if I'm not working with it yet. Now let's multiply through. We've got a binomial times binomial, let's FOIL it. So that's going to be, open bracket, open parentheses. First of all, b1 cosine beta t. So make sure you keep your b's and your betas distinct. b1 cosine beta t, that's a real function. I like this one. This one's totally real, not complex. The only other totally real thing I'm going to get out of this is when I do last times last, because I've got an I squared. An I squared, of course, is -1, and that gets me into a real thing. So I'm going to say minus b2 sine beta t. And then close off my parentheses. That's the real stuff. Now I'm going to say plus I and collect the imaginary stuff. The inside one will be b2 cosine beta t. The outside one will be plus b1 sine beta t. Close that parentheses, close the brackets, don't forget the e to the alpha t. So double check my work, make sure I didn't lose anything. Okay? Similarly, let's do the second one. If I work out k sub 2e to the lambda 2t, I get, and this time I'm not going to work through the details, I'm just going to write them down. Feel free to check it if you like. It would turn out to be this, open brackets, open parentheses, b1 cosine beta t minus b2 sine beta t, close parentheses, minus I times, new parentheses, b2 cosine beta t plus b1 sine beta t, close parentheses, close brackets, e to the alpha t. And as you compare those two things, what do you notice? They're practically the same except for right here, a minus instead of a plus, but all the other details come out to be exactly the same. So, are we better off than we were before? Well, maybe a little, because we at least have gotten all of the complex numbers out of the powers down into the baseline. Trouble is, these are still complex. I'm still complaining. I don't like it. So it's a little better, but we still have complex solutions. I don't want complex solutions. On the exam, I will say find real solutions. So this would not make me happy. So how can we take this and get get real solutions out of it? And what rescues us, believe it or not, is the principle of superposition. Did we begin with something linear and homogeneous? Well, I don't have it up here, but you know we did. It was the x prime equals ax, linear homogeneous. Principle of superposition we can apply anytime we like. So can you think of what linear combination we could do to this and that solution to get something real? Principle of superposition says if I do linear combination solutions, I get more solutions. So what specific thing could we do, Rudy?
Add them together with the same coefficient.
There you go, we can add them together. If we add them together, we keep this part, which is totally real. We get rid of this part, which has the i's in it. And specifically, when we add them together, we get twice this. So I'm going to write everything out so that you have it in your notes. Since the system is linear and homogeneous, we can apply the POS, principle of superposition. Next phrase will be obtaining the following real solutions. Obtaining the following real solutions. So essentially, what I want to do is add those two things, but that's going to give us twice what we, that expression there. The POS also allows us to multiply by constants if we like. Can you guess what constant I would like to multiply by? Instead of having 2 times all that b sine cosine stuff, why not just have 1? So I would multiply by 1/2. So my first solution that I'm going to propose as a nice real solution is going to be half the sum of those things, k1 e to the lambda 1t plus k2 e to the lambda 2t. And when I add up those two things and then multiply by a half, I will get b1 cosine beta t minus b2 sine beta t all times e to the alpha t. And that is a lovely real solution. But that's not enough. If I'm beginning with a 2 by 2 sort of a thing, which is kind of implied here because I'm working with two eigenvalues, two eigenvectors, I need a second solution that's linearly independent of that one in order to generate everything I need. So can you think of any other linear combination we could do here that would get us a linearly independent real solution? Instead of adding the two, I could subtract. What's the trouble with that? If I subtract, this part wipes out, and I get this except it's multiplied by 2i. Not good enough. Still has a complex number in it, but what constant could I multiply by?
1/2 I.
1 over the 2i. Something like that to get rid of the i's. Perfectly okay. So my second solution, which will be linearly independent of the first, I'm going to select doing 1 over 2i times k1 e to the lambda 1t minus k2 e to the lambda 2t. Principle of superposition says, excellent, it's still going to be a solution, and I feel better because then I get something real. And that real thing I get is b2 cosine beta t plus b1 sine beta t all times e to the alpha t. And this satisfies me because now I have two linearly independent solutions that should generate everything I need. Any questions on the mathematical derivation there? It's very clever, probably similar to something you've seen before. And now we're ready to summarize case 2. So this is basically just going to be a summary of what we've already done. I'm not going to write anything new here. If I begin with complex conjugate eigenvalues, alpha plus or minus beta I, with eigenvectors, b1 plus or minus b2i, I get the following. Linearly independent real solutions with emphasis on the real. Even though the complex numbers came into it, we were able to get rid of them. And they are, and again I'm just repeating now, x1 of t equals b1 cosine beta t minus b2 sine beta t times e to the alpha t. And the second one, again, just repeating, b2 cosine beta t plus b1 sine beta t e to the alpha t. So write those down carefully because I have a feeling you'll want to put those on your little 3x5 note card before the next exam. No need to memorize those, may as well write them down. Before we do an example, and that's of course what we're headed toward, there is one very common mistake that people make when they apply these formulas. Because basically they're not that hard to apply. The hard part again is finding the eigenvalues and eigenvectors. That's where the real work comes in. Once you have those, then you just kind of pop them all into the formulas. But there's one error in thinking that some people will do, and that is this. You tend to think that for x1, you use lambda 1 and k1. And for x2, you use lambda 2 and k2. So you think that you've got to throw in some extra negatives when you do the second solution. Don't do that. All of those extra negatives have already been put into this derivation. They're here, they're other spots. They are there. They've already been incorporated. You don't need to think, oh, second solution, I've got to throw in more negatives. So my note, I'll phrase it this way. Once alpha, beta, B1, and B2, those are all the ingredients you need. Once they have been identified, use them for both X1 and X2. Don't feel like you've got to throw in additional negatives to go to complex conjugates. It's already been done to get those formulas. All right, we have a little bit of time for an example. I keep using different notation for the same stuff. I just want you to be familiar with all the ways to do it. So last time I used the dx, dt, and dy, dt notation. This time I'll say x prime, y prime. Sometimes I might say capital X prime. Equals 7, -5, 4, 3, xy. So this time I've already taken it out of the systems form and put it into the matrix form for you. But either way, that's not a big deal. Either way, you immediately go for those coefficients. You know those are the things that are going to get you your solutions. And you may notice we've done this example before as well. This was example 3 from section 8.8. That's basically because I don't want to take time today finding eigenvalues and eigenvectors. We have found these before. So the eigenvalues were 5 plus or minus 4i. We don't even have to worry about the minuses. Again, those have already been put into the formulas. All we have to think about are first eigenvalue and the first eigenvector. So if lambda 1 is 5 plus 4i, then what's alpha and what's beta? Alpha is 5 and beta is 4. And again, when you do the second solution, don't go to beta equals -4. Don't worry about that. It's already been put in. And the eigenvector that corresponded to that was 1 plus 2i2. And this B1 plus B2i thing basically says we just want to separate that out into its real part plus its imaginary part. So the real part would have what components? 1, 2, and the imaginary part? 2, 0. And notice that our B1 is just that thing, B2 is just that thing. The I is separate. That's not part of B2. There would be another great place to make a mistake. The I is not part of the B2. The B2 is what's in front of the I. And once we have those ingredients, we just fill in the details of the formulas. So nothing tricky about it. You just pop stuff in. So you can write down x1 of t equals, and away we go. x1 of t equals, according to the formula, big parentheses, we want b1 cosine beta t minus b2 sine beta t. So b1, 1, 2, cosine, let's see, beta again was 4, so cosine 4t, minus b2, that's the 2, 0, sine beta t, sine 4t, all times e to the, that's supposed to be alpha t, alpha is 5, so e to the 5t, and x2t using the second formula is, this time we begin with b2, so that's 2, 0, cosine beta t, cosine 4t, plus 1, 2, there's the b1, times the sine of beta t, sine 4t, all times e to the 5t. And even though these things look really wide, this is just a column vector. One function here, one function there. It's a 2 by 1 vector. I kind of like to mush it all together. So that's going to be a 1 cosine 4t minus 2 sine 4t. So cosine 4t minus 2 sine 4t, all times e to the 5t. That's the top function. That's the little x of t. The bottom function is 2 cosine 4t e to the 5t plus 0. And similarly, the bottom one mushes together like this. 2 cosine 4t plus sine 4t e to 5t and 2 sine 4t e to 5t. And the checks here would be complicated, but you could make them work. We don't have time to do a check. The last thing I want to do is apply that theorem to and say that because we have two linearly independent solutions for a 2x2 system, they will span. So big X will be C1x1 plus C2x2. In other words, we have everything. We have all solutions from those. And we are out of time, so I have to stop talking. Thank you. We have case 3 left, repeated eigenvalues for Thursday, and then we get to draw pictures.